Hello class. Today's topic is on rates of change. Given two covariant quantities, a rate of change is an amount of change in one quantity per unit change in the other quantity. Find two different rates of change in each scenario. The first scenario is we hire a repairman. The two covariant quantities are time worked by the repairman and the cost for the repairman's labor. As time changes, you expect cost to change, and so we call these quantities covarying. They change in tandem. Also notice that when time is zero, so if the repairman works 0 hours, the cost will be $50. That is a flat fee just for coming out to provide a service. And then if the repairman works 4 hours, the total cost will be $130. So one rate of change that we might calculate would be the change in cost divided by the change in time. Doing this, we can calculate as follows. We'll take the second cost minus the first cost, this will be the change in cost, and divide that by the difference of the two times. So in this case, it would be $130 minus $50 all over 4 hours minus 0 hours. This gives me 80 over 4, which is 20. Now the unit on this rate of change is going to be the unit of cost divided by the unit of time. So this would be dollars per hour. So this is how much the repairman charges per hour once he or she arrives. You can also be charged per partial hour. So if the repairman works for 30 minutes, you will be charged half of $20 or $10. Another potential rate that we can consider is the reciprocal of this, which would be change in time, so T2 minus T1, per change in cost. This rate of change will be 4 minus 0 divided by 130 minus 50. We get 4 over 80, which is 1/20th. And notice the answer here is the reciprocal of the previous answer. But this time the unit will be hours per dollar. So if you're interested in analyzing the scenario on how much time can I buy for every dollar, then this tells us that you can buy 1/20th of an hour of the repairman's time per dollar that you offer. In the other scenario, you fill equal containers with water. X is the number of containers and W is the weight of water, and these covary together. If you change X to different numbers, you expect W to change as well. Now, when X is 0, meaning you fill 0 containers of water, then you expect the weight to be 0. But when X is 6, if you fill 6 containers, then the weight becomes 90. So one rate of change that we can find would be the change in water, so let's do W2 minus W1, divided by the change in containers, so X2 minus X1. And this gives me 90 minus 0, or just 90, divided by 6 minus 0, which is just 6. And 90 divided by 6, well, 90 divided by 3 is 30, and 30 divided by 2 is 15. So we get 15. And the units here would be the units of W divided by the units of X. So this would be pounds, LBS is pounds, per container. So basically, each container can hold 15 pounds of water. And all the containers we're assuming are equal. Also, keep in mind you can fill partial containers. So if it's 15 pounds per container, then half of a container would hold 7.5 pounds, etc. But a second rate we can consider was the reciprocal. So we do X2 minus X1 divided by W2 minus W1. And we can say this gives us 6 over 90, or 1/15th. And the units here would be containers per pound. So in other words, 1 pound of water will fill 1/15th of a container, because it's 1/15th container per pound. Okay, let's go to the next page. Graph the data below with time as the horizontal axis. Find the slope of the line connecting the points. Include units on your answer. So this is the same scenario as scenario 1 from the previous page, that we hire a repairman, and the data is the same. But this time we're going to make a visual connection. So we are told that the horizontal axis should be time. So let me go down here and label time as the horizontal axis and then put its unit of measure. This is measured in hours. And therefore the vertical axis is going to be cost, and that's measured in dollars. The two data points are 0, 50. So we have a point right here. And then 4, 130. That would be this point over here. If we were to draw a line segment connecting these 2 points, then the slope of this line segment is going to be one of the two rates that we calculated above. And in the traditional sense, when we calculate slope, we usually do the change in the vertical axis divided by the change in the horizontal axis. So it's the rise over the run as we're used to. So let's go ahead and assume that when we calculate slope in a visual context, that we're always going to default to a change in y per a change in x. So in this case, y is the cost, so will be a change in cost divided by a change in x, and x is time, so we'll say delta t. This will give us one of the two rates that we calculated above, and in this case, the change in cost was the 80, and the change in time was 4, and it gave us the 20, and the units here would be the vertical unit divided by the horizontal unit, so dollars per hour. Okay, let's go to the next page. Given a function f of x, the slope of a line connecting the points a, f of a and b, f of b is called the average rate of change of the function over the interval from a to b. Such a line is called a secant line. The function below models the height of an object measured from the ground and measured in feet as a function of the number of seconds that have elapsed. Find the average rate of change between 3 and 8 seconds. All right, so time is the horizontal axis again, but this time measured in seconds. And the vertical axis is height, measured in feet. Now this graph here is not the path of the object. This object is going straight up, it's changing height. The horizontal axis is not a spatial dimension, it's a time dimension. So at different times we get different heights, but the object is really moving straight upwards. When time is 3 seconds, we can find out what the height of the object will be by plugging 3 into the function. But for now, I can say that this is simply going to be, the input will be 3 and the output will be f of 3 using function notation, and we'll calculate f of 3 in a moment. So that's that point right there. The second time in question is when time is 8 seconds. So we have 8 seconds, and we have another point here. Its coordinates are going to be 8, f of 8. And we'll calculate f of 8 in just a moment. Now the line that connects these 2 points, let me draw that next, and let me make it a different color. This is called the secant line. The slope of this line is going to be called the average rate of change in this function between these two different t coordinates, between time 3 and time 8. And we can calculate the slope in the following way. It's going to be f of 8 minus f of 3 all over 8 minus 3. So we do the change in the y-coordinates divided by the change in the x-coordinates, or t-coordinates, if you will. So x stands for time. So I'll sometimes call it x, sometimes call it t, but every time I say x or t, I'm referring to the input coordinate. All right, plug 8 into the function. So the function rule is provided. It's right here. We're going to plug 8 into this function rule and calculate the output. So when time is 8, when x is 8, 8 squared is 64, double 64 is 128, and then add 10 is 138. So this is 138 measured in feet. I'm going to leave the units off, but just keep in mind that that's a foot measurement. Minus, and now let's plug time 3 into this function rule and calculate the height. 3 squared is 9, 9 times 2 is 18, and add 10 is 28. And then we're going to divide that by 8 minus 3, which is 5, and that's measured in seconds. So the numerator is in feet, the denominator is in seconds. Keep that in mind. 138 minus 28 is 110. And we want to divide 110 by 5, and that will give me 22. And the measurement now, we'll put a unit on this. This will be feet per second. Notice that this is a unit of velocity. It's the rate of change of position with respect to time, in this case, measured in feet per second. Now, this object is not always traveling 22 feet per second. This is an average rate of change. The object climbs from 28 feet to 138 feet, and it does that in the space of 5 seconds. But it's not always going the same speed. In fact, this object is accelerating upwards. Its velocity is changing. Imagine being in a car and hitting the gas and watching the speedometer change. Your velocity is changing. What we can do is say, okay, well, how far did I go and how much time? And then ask yourself, well, what's my average speed or average rate of change? So that if I was going at steady speed, I can cover the same amount of distance in the same amount of time. So on average, this object was traveling 22 feet per second over this time interval from 3 to 8 seconds. Okay, let's go to the next page. Find two different expressions for representing the average rate of change of the function over the interval 3 to b. So b is now general. We're going to keep 3 fixed. So let's go ahead and find 3 on our time axis again, right here, and plot this point. And we've already calculated it was 3, 28. And then b is going to be a right endpoint that we're going to keep arbitrary. So I'm just going to draw a random vertical line and say that this is located at time b. Now the best I can say for the coordinates of this point are going to be b, f of b. And we want to find the slope of this line. The slope of this line is going to be, we'll do the change in y coordinates, so f of b minus 28, which is f of 3. I'll write f of 3 for now, but I'll change it to 28 in a moment, over the change in x coordinates, b minus 3. Now in this context, we can actually simplify this algebraically because we happen to know the rule of the function f. So when I say what's f of b, you just take this rule right here and change the x that you see right there, change that to b. So we'll get 2b squared plus 10. So as I continue to work with this, we get 2b squared plus 10. That's what f of b is. And then minus, and then f of 3 we calculated already to be 28, and then divided by b minus 3. Now we can continue to simplify this algebraically. So we have 2b squared plus 10 minus 28, so I can add the numbers and get minus 18 all over b minus 3. Now notice I can factor a 2 out of the numerator. That leaves b squared minus 9 all over b minus 3. Now notice that there's a difference of squares in the numerator. B squared minus 9 factors to b minus 3 times b plus 3. And then further notice that our b plus 3 factors can cancel. So we get, in the end, just 2 times b plus 3. And this is a simplification of our expression. Now this is a formula that tells me the slope of the secant line, and it's dependent on where b is. Let me go ahead and draw that secant line real fast. There it is. So there's the secant line that connects the 2 points. The slope of that line can be calculated by simply doing the calculation 2 times b plus 3, where b is the location of the second x coordinate. Let's go over to Desmos and show how to do this with technology. Now I've already typed in the function. I typed in f of x equals 2x squared plus 10, and it gives me this graph. I want to change the vertical scale because when time is 8, you can see it's way up there. So I'm going to change the vertical scale just so we can see a little bit more of the graph. There we are. Now one point that we want to highlight here is 3, f of 3. So let's make a point, 3, and then f of 3. And if you want, you can put a label there. So there's the first point in question. Now the next point that we want to do is general. We're going to say b, f of b. So b, f of b. Now notice it says, would you like to create a slider for b? And you should say yes. So just click that and create a slider. Now b becomes a slider that I can move around, and notice that it makes a point somewhere on the curve depending what b is. So if I park b at 4, then that red point is the point that has an x coordinate of 4. Now let's calculate the slope between the red and the black points. And let's call it m. So m equals, and then we do f of b minus, and then I could say f of 3, or I could just type in 28. Let's just type in 28 because that's what f of 3 is. And then we divide all of this. Let me put all that in parentheses and then say divide. Divide all of that by b minus 3. And there's the slope of the line connecting the 2 points. If you want the fraction form, you can show it as a fraction or as a decimal, you choose. Now as b changes, that slope changes. Now if you're interested in also drawing the secant line, let's go ahead and do that. We're going to use point slope form, which is y minus the y coordinate. So y minus, and let's use the black point as our anchoring point. So y minus the y coordinate at that point is y minus 28 equals, and then the slope, I'm just going to use m for the slope because we want it to change as I drag the slider, and m has already been assigned above in line 5 to calculate correctly every time I move the slider. So if I just use m again, it'll borrow the m calculation from above, and then parentheses, and then we do x minus the x coordinate. So x minus, and then the x coordinate of the black point is 3. And let's change the color of this secant line to orange. So now we have a secant line that's drawn, and as I move b to different values, you can see the secant line adjusts automatically, and the slope of that orange line is always calculated automatically for us. Now what I'm going to do is I'm going to type into Desmos this simplification and show you that this simplification, this calculation, 2 times b plus 3, also gives us the correct slope as I change b to different values. So it was 2 times and then b plus 3. And notice that that calculation, we get 22.8, which is the same thing that matches the m above. And as b changes, the two slope calculations always match. Okay, let's go back to our notes. Now, the instructions did say find 2 different expressions for representing the average rate of change. So I'm going to show you next is a different way to do this. Let's change this b here and change this point up here. And instead what I'm going to do is I'm going to introduce a variable that's the distance between the 2 vertical dashed lines you see in our picture. Let's call this distance h. So we're going to use h to stand for how far apart the 2 vertical lines are. And so if we're starting at the left endpoint is 3, and then I go to the right h, instead of using b to represent this second vertical line on the right, and this line right here, we're going to represent it by saying we started at 3 and I went to the right h. So it's 3 plus h is the new x coordinate. So this second point here, its coordinates will be 3 plus h will be the input coordinate, and the output coordinate will be you plug 3 plus h into the function, f of 3 plus h. Okay, for our second approach here, I'm going to calculate the slope by doing f of 3 plus h, that's the first or the second y coordinate, minus f of 3, which is the first y coordinate, so it's y2 minus y1, all over the change in the x coordinates. So 3 plus h is the second x coordinate minus 3, that's the first x coordinate. Now we're going to manipulate this expression. Notice down here that the 3's will cancel, leaving just an h, and then the other thing we need to do is calculate what f of 3 plus h is. So we look over here at the rule of our function, and we're going to change the x right here to 3 plus h. And use parentheses. So we wind up getting 2 times 3 plus h squared plus 10. So this f of 3 plus h is given by this expression right here. And that's only part of our numerator. Now we have to, from that we have to subtract f of 3. Plugging in 3 into the function, we do get 28, as done before. And this is all over a simple h, because the 3's cancel in the denominator. All right, the next thing we want to do is actually FOIL this expression here and also combine these numbers here into a new number. So let's talk about FOILing this. 3 plus h quantity squared means you're really doing a 3 plus h times another 3 plus h. So we do 3 times 3 is 9. 3 times h is 3h. 3 times h is another 3h. And then h times h is h squared. So that becomes 9 plus 6h plus h squared. So back up to our work here, we have 2 times 9 plus 6h plus h squared. And now we have the plus 10 and the minus 28. That gives us minus 18. And this is all over h. All right, continuing to simplify, distribute the 2 next. So that gives us 18 plus 12h plus 2h squared. And then minus 18 all over h. Notice the 18's cancel each other. So we just get 12h plus 2h squared all over h. And finally, I can factor out an h from the numerator. I could also factor out a 2, but I won't. Just factoring out the h from the numerator so that I can cancel it with the h from the denominator. So in the end, we get just 12 plus 2h. And let me connect all these with equal signs, like I did before. So 12 plus 2h is a way to calculate the slope of the secant line if all you do is tell me h, where h is the horizontal distance between x equals 3 and x and the next point, 3 plus h, the next x coordinate. You tell me the horizontal distance between these two vertical lines, and 12 plus 2h will calculate the slope of the secant line. Okay, let's go back to Desmos. So the function in question, we're going to calculate the slope using this new formula. So m equals And we have f of 3 plus h, and then minus just f of 3. I could just type a 28 here, but I'll go with function notation still. And I'm going to put all of this in parentheses so I can divide all of it by just h. And then my next line uses m as the slope, but it needs a slider for h. We haven't said what h is yet, so go ahead and add that slider for h. We're prompted here in line 4 to do that, so create a slider. And then h can be dragged to different values now, and you'll see the slope changes. But I don't currently see a second point, so I'm going to go up here and insert a space and plot the second point. The second point, its coordinates were 3 plus h, comma, and then f of 3 plus h. And there's that second point in blue. Now as I change h, we can see the 2 points and we can see the secant line connecting them. And notice h can also go negative, meaning just that the blue point's to the left of the black point. Let's go ahead and reveal the coordinates of that blue point as well by toggling on the label. And let's park h at 3 and just pause and reflect what's going on here. Now look at the two points, the black point and the blue point. Horizontally, they are 3 units apart, right? Focus on the x coordinates, 3 and 6. So time-wise, these are 3 seconds apart. And h tells us that gap. When h is 3, the 2 points are 3 units apart. If I drag h over to 4, now the 2 points are 4 units apart horizontally, so 4 seconds apart. And when h is negative, it just means we go left of time 3. And the slope calculation changes automatically. Looking back at our work over here, we said that we can also use this 12 plus 2h to calculate the slope. This is a simplification of this expression that we have up here, that we typed this into Desmos, basically, and having Desmos do all the work for us, but I can also type in this and just use this instead as a way to calculate the slope when I know what h is. So going back to Desmos, let's just type that 12 plus 2h. And notice that this calculation gives me the same slope as the m calculation above, and even when I change h to different values, they're always the same. Okay, let's go to the next page. Given a function f of x, the difference quotient is defined as follows. F of x plus h minus f of x all over h. Now what this is doing, but in more general terms, let's say that we have some sort of a function, f of x. We're going to pick 2 different x coordinates. The first one we're going to just call x, and then we're going to go to the right h units, kind of like we did before, or to the left, depending if h is positive or negative, but in our image, we'll draw it to the right, so h being positive. We'll go to the right h and get to a new x position called x plus h. Right, then these coordinates here would be, the first point would be x comma f of x would be its coordinates, and the second coordinates would be x plus h comma f of x plus h. And then we will draw a secant line between them and then calculate and then set up the slope formula. So f of x plus h, which is the first or the second x coordinate, minus the first x coordinate, f of x, all over, and then we have x plus h is the second x coordinate minus x, which is the first x coordinate. And you'll notice that the x's in the denominator cancel, leaving just an h. Hence, we get this expression you're seeing up here, which is called the difference quotient. For the function below, set up and simplify the difference quotient. Now, this function is the same function we've been working with, and the work we do here is going to be very similar to the work we did right here, except we're not going to use 3, we're going to replace the 3 basically with x, keep it general still. So the difference quotient is f of x plus h minus f of x all over h, and the tricky part is going to be calculating this f of x plus h part. And we do that by using the rule of the function. So take this function right here and simply change this x right here and any x you might see in the function rule, change them all to x plus h's and use parentheses. So we're going to get 2 times parentheses x plus h and then squared and then plus 10. So the 2 red parts align with each other. And then we do minus and then f of x. Now f of x, let me put that in green. F of x is just the rule exactly as you see it. So this rule here is f of x, and we're going to subtract this rule from the red portion. So subtract, and then we write the function rule again. So 2x squared plus 10. This is f of x. But make sure you put it in parentheses because it's being subtracted. And that negative will need to distribute. And this is all over h. So this part right here is just f of x. Okay, now we're going to do a couple things here. We're going to FOIL x plus h. That's going to give me 2, and then foiling x plus h, we get x squared plus 2xh plus h squared. I'll leave it to you to FOIL that and confirm that. And then plus 10. And then the other thing we're going to do is distribute the negative across the green. So we're going to get minus 2x squared minus 10. And this is all over an h. Now a couple things we're going to do next. Notice the 10s are going to cancel each other, so I won't need to write them a second time. And let me also shrink this work down and kind of move it out of the way. We'll probably need a little bit more space here. And the other thing is distribute the 2. So we have a 2x squared plus 4xh plus 2h squared. And then the 10's canceled, and then we do have that minus 2x squared still, and this is all over an h. Now notice the x squares cancel each other, so this takes us to now just 4xh plus 2h squared all over an h. Now like before, look back at the previous example, that's kind of like getting to this point right here. The numerator, every term in the numerator had an h, so I could factor an h out. Well, that's true in this case here. Every term in the numerator has an h, so I can factor the h out as my next step. I could also factor out a 2, but let's just factor out the h. So that leaves me 4x plus 2h all over an h. And then the h's cancel. So then the final simplification is 4x plus 2h. And we'll stop right here. And this is a simplification of the difference quotient for this particular function. So practicing doing this is a skill you're going to want as you move into calculus. And for now, for this class, we just stop right here. We explain what the difference quotient is, and then how to set it up given a particular function, and then how to simplify it down to a more simple expression. And you'll notice that in this case that there's x's and h's both in our answer. That's not always the case. Sometimes there will not be any x's, but there will always be an h in your answer. Okay, let's go to the final page. Given a function f of x, a tangent line, if it exists, is a line which passes through a point a comma f of a and which indicates the rate of change of the function at that point. This rate of change is called the instantaneous rate of change of the function at x equals a. For the function below, draw the tangent line at x equals 3. Then approximate the instantaneous rate of change of the function at this time. So this is the same function we've been analyzing. Let's go ahead and go down to x equals 3, which is right here. And we did have a point here. It was 3 comma f of 3, and f of 3 we calculated already was 28. So 3 seconds into this, the object is 28 feet high. And what we're going to do is draw what's called a tangent line. A tangent line is a line that passes through this point and indicates the direction of the curve. So I'll draw some lines here that pass through the point but do not indicate the direction. Like this line right here is not a tangent line. A tangent line is a line that you would expect to see if we zoom in really far. It's a line that pretty much looks like the curve at that point. So it'd be a line that looks something more like this. It doesn't go through the curve, it just intersects the curve at that point, and it indicates how steep the curve is at that point. This is called the tangent line. Now, to find the slope of a tangent line is a tricky thing, because a tangent line, we only know one point on the tangent line. So I can't do my conventional y2 minus y1 over x2 minus x1. But we can look for patterns as I do secant lines, and I let the 2 points get closer and closer to each other. We're going to make a second point by going h units to the right. So I'll draw a second point. We'll h units to the right. We're going to find the slope of the secant line, and then we're going to let h get closer and closer to 0 and see if we can look for a pattern. So I'm going to borrow the work that we did up here. All of this work we would want to do again. So I'm just going to copy and paste it down here in our notes. Let me shrink it down a little bit. And this was a formula that gave me the slope of the secant line. We'll say m of secant line. And we're going to use this simplified version to calculate it, this 12 plus 2h. So we're going to pick different h's. Maybe I'll make a table, and then we'll calculate the different slopes. So when h is 1, for example, just plug a 1 into this statement, and notice you get 12 plus 2, you get 14 would be the slope. And we're going to let h shrink to 0. Now visually what's happening here, if we go back to Desmos, is we're going to let h be maybe 2 we'll let h be 1. Notice it gives us a slope of 14. Let me zoom in here. And we're going to let h get closer and closer and closer to 0, and you'll notice that the orange line gets closer and closer to a tangent line. Now we can't let h actually be 0, because if you do, there's no longer 2 points and all the programming here falls apart. There's only 1 point and it can't make a line with just 1 point. But we're going to look for patterns. As we get closer and closer and closer to 0, we expect that the slope of the secant line will get closer and closer to the slope of the tangent line. So if I shrink h to maybe 0.1 and plug that in, we get 12 plus 2 times 0.1, so we get 12.2 basically. If I shrink h to 0.01, we're going to get 12.02 as the slope of the secant line. If I shrink h to 0.001, we're going to get 12.002 as the slope of the secant line. And as this gets closer to 0, as this approaches 0, this slope over here appears to be approaching 12, which is our prediction of what the slope of the tangent line is going to be. So we're going to say the slope of the tangent line is 12. Now let's put a unit on this. This would be all the slopes here. The vertical unit is measured in feet. The horizontal unit is measured in seconds. So this would be feet per second. This is an instantaneous rate of change of the object at this time, at time 3. It's like you could imagine the speedometer of this object moving up is changing, but if you take a picture at 3 seconds and look at the speedometer, you would see 12 feet per second. That's how fast the object is moving at that moment in time. Of course, it speeds up at the very next moment in time. You would expect to see a different velocity. This velocity is not constant. I should also mention that our velocities are 12. They're positive numbers suggesting motion upwards. Velocity is a speed with a direction. So positive velocities are upwards and negative velocities are downwards. In this case, the object is moving up. So that's why all of our velocities have been positive numbers. But it's entirely possible to have a negative velocity indicating that we're going in the negative direction. And in this case, that would be down. Okay, this concludes our discussion on rates of change.